to first overdrawn, and the third one we observed as a least intense line, that is due to second overdrawn. But if you consider the vibrational spectrum of polyatomic molecule, the spectrum will be quite complex. Indeed, the IR spectrum of a molecule of a reasonable size is quite complex and it is almost impossible. However, with a little understanding of the possible vibration modes, their IR activity or inactivity, and the concept of characteristics group frequency, we can make enough leads to observing the spectral complexity of the molecule. So here we will discuss what are the different modes of vibration and also the degree of freedom for polyatomic molecule. A diatomic molecule has only one possible way of executing vibrational motion because there are only one bond and the molecule is linear. We know that every diatomic molecule is linear. So as the molecule is linear, suppose if you consider HBr molecule, so this is a linear molecule, so only one type of vibration will be possible. A molecule containing more than two atoms or and then more than two bonds, also these bonds may be at angle with one another. For example, if you consider a triatomic molecule, for example water molecule, we know that what the shape of the water molecule is bent or V shape. This is the shape of water molecule. This is not a linear molecule and the bond angle is 104.5. The bond angle is 104.5. Such a molecule can vibrate more than one possible way. This molecule will vibrate in a single way. But the water molecule, which is a non-linear molecule, will undergo vibration at more than one possible way. Like both the bonds of a molecule that may vibrate symmetrically, that may vibrate asymmetrically, so that will give rise to different types of vibration. So how symmetrical vibration and asymmetric vibrations are possible for non-linear molecules, that will discuss later. So here first we'll discuss what are the degree of freedom. For a molecule containing n atoms, we need to specify 3n coordinates. 3n coordinates, that means for each atom there will be three coordinates, x-axis, y-axis and z-axis. So that's why if a molecule contains n number of atoms, then the total number of coordinates will be, then there will be 3n coordinates. This fixes all the bond length and the angles of the molecule. We may say that the molecule has 3n degree of freedom. So, if the molecule contains n number of atoms, the total number of degree of freedom will be 3n degree of freedom. And again, we know that out of the total degree of freedom of a molecule is due to translational degree of freedom plus rotational degree of freedom plus vibrational degree of freedom. And again, we know that the three-dimensional space, the position of a molecule can be specified in terms of three coordinates, and hence the total number of translational motion there will be 3, and hence the translational degree of freedom will be 3, one along x-axis, another along y-axis and another along z-axis. So the total number of translational degree of freedom for any type of molecule will be 3. Now if we subtract that translational degree of freedom from the total number of degree of freedom, that will become 3n minus 3, and hence for every molecule there will be 3n minus 3 degree of freedom for rotational and vibrational motion. That means for a molecule, the number of vibrational degree of freedom plus number of rotational degree of freedom equals to 3n minus 3 if the molecule contains n number of atoms. Now coming to how many rotational degree of freedom. The rotational modes depends upon the geometry of the molecule. A linear molecule can rotate around only two of the three axes. If the molecule will be linear, then the molecule can rotate along, suppose here we are considering HBr molecule. The HBr molecule is a linear molecule, and let the bond along the hydrogen and bromine atom will present on the x-axis. So if you rotate the molecule along x-axis, there will be no change in the molecule. But if you rotate the molecule along y-axis or along z-axis, then the molecule will undergo change. So a linear molecule can rotate around only two of the three axes. If the molecule lies along the x-axis, then it can rotate only around the y and z-axis, and we will try to rotate the molecule. If we try to rotate the molecule along the x-axis, the position of the atoms do not change. So we therefore say that linear molecules can have only two rotational degree of freedom along with three translational degree of freedom. However, for a non-linear molecule that may, if the molecule will be non-linear, that may rotate along the x-axis, along the y-axis, along the z-axis. So now, before that we have discussed that the total number of translational degree of freedom for any type of molecule. First, we have discussed if the molecule will contains n number of atoms, then the total number of degree of freedom will be 3n. So, out of the 3n total number of degree of freedom, the number of translational degree of freedom will be 3, and hence the number of rotational degree of freedom plus number of vibrational degree of freedom will be equals to 3n minus 3. Now again for rotational degree of freedom, if the molecule will be linear, then the number of rotational degree of freedom will be 2, and if the molecule will be non-linear, then the number of rotational degree of freedom will be 3. And hence from that we can calculate the number of vibrational degree of freedom. If the molecule will be linear molecule, then the number of vibrational degree of freedom equals to 3n minus 3 minus 2. That is 3n minus 3. So we left with 3n minus 5 degree of freedom for a linear molecule. That means 3n minus 3 minus 2 minus 3 for translational minus 2 for rotational. So the total number of vibrational degree of freedom for a linear molecule is 3n minus 5. And similarly, the total number of vibrational degree of freedom for a nonlinear molecule equals to 3n minus 3 minus 3. The first 3 is due to translational and the second 3 is due to rotational. So the remaining vibrational degree of freedom will be equals to 3n minus 6 if the molecule will be nonlinear. And if the molecule will be linear, the number of vibrational degree of freedom equals to 3n minus 5. Now, if we consider the total number of vibrational degree of freedom or the total number of vibrational modes for carbon dioxide molecule, we know that the shape of carbon dioxide molecule is linear in nature. So, this is the structure of carbon dioxide molecule. So, that is a linear molecule. And here, 3 atoms are there. So, the total degree of freedom, total modes of vibration, total degree of freedom equals to 3 into 3 equals to 9. That is equals to 9. And as the molecule is linear, the number of vibrational degree of freedom, equals to 3n minus 5. 3n minus 5. That is equals to 9 minus 5. That is equals to 4. Now, if we consider water molecule, we know that water molecule is non-linear in nature, that is angular or V-shaped, and hence the number of vibrational modes or the total number of vibrational degree of freedom equals to the number of vibrational modes or the total number of vibrational degree of freedom equals to 3n minus 6. That is equals to, in place of n you can put 3 because in water molecule 3 atoms are there. So 9 minus 6 equals to 3. So for water molecule, the number of vibrational modes equals to 3. For carbon dioxide molecule, the number of vibrational modes equals to 4. Now coming to normal modes of vibration. A molecule can vibrate only in certain modes known as normal modes. So there are two types of normal modes of vibration for a polyatomic molecule. So these are stretching vibrational modes and bending vibrational modes. So here we will discuss what is stretching vibrations. In stretching vibrations, the atom move along the bond axis so that the bond length increases or decreases at a regular interval, and the stretching vibration.
Hello. हेलो जितेंद्र जी। सर है कि चले गए? हेलो।
हेलो।
सर चले गए ना?
क्लास ओपन हो गई क्या? हाँ
Hello,
सर चलेगी। हाँ आई सर।
hello.
जी सर, जी सर।
Okay. So now it is okay, no problem.
यस सर।
So first we'll discuss out of the two normal modes of vibration, the two normal modes of vibrations are stretching vibrations or stretching vibrational modes, and the second normal modes of vibration, that is called bending vibration or bending vibrational modes. So first we will discuss about the stretching vibrations. So the stretching vibration, in the stretching vibration, the atoms move along the bond axis so that the bond length will increase or decrease at a regular interval. Now, the stretching vibration again divided into two types. The first one is symmetric stretching and the second one is asymmetric stretching. So now coming to what is symmetric stretching and what is asymmetric stretching. Thus, in symmetric stretching of a triatomic molecule, both the bonds are connected to a common atom, either elongate or contract simultaneously. So here you see, here that is symmetric stretching. Now suppose this is the atom, central atom A, and that is connected to two other atoms B. If the left hand side atom B will stretch into left hand side, and the right hand side atom B will stretch into right hand side, that is called symmetric stretching. And here this is asymmetric stretching. That means if the left hand side atom will undergo compression and the right hand side atom will undergo stretching, that is called asymmetric stretching. And similarly, so here both the bonds are connected to a common atom that either elongate or contract simultaneously. In case of asymmetric stretching, if one bond is stretched, the other bond will be compressed or vice versa. So the stretching vibrations along with the bending vibrations are shown in the below figure. For a linear and angular molecules AB2 types, the arrow attached at each atom show the direction of the motion during the half of the vibration. Now this is the symmetric stretching modes for non-linear molecule. That means atom will stretch into this direction and another atom will stretch into this direction. That is the symmetric stretching for non-linear molecule. And here this one is asymmetric stretching. That means one atom B will stretch and another atom will undergo compression. So for one atom the bond length will elongate and for another atom the bond length will shorten. So this is called asymmetric stretching for non-linear molecule. Now coming to the bending vibration. So the bending vibrations are said to occur when there is a change in bond length between the bonds connected to a common atom. In some cases, the movement of group of atoms with respect to the remaining atom in a molecule is also cause the bending vibration of a polyatomic molecule. A linear triatomic molecule has two bending vibrations as shown here. So this is a linear triatomic molecule. So there will be two bending vibrations. You can see the two atoms will bend towards this and the central atom will bend to backward. So that is one type of bending vibration. And the other type of bending, so that means the atoms will bend along suppose the linear molecule will present in x-axis, then the atoms will bend along the z-axis. And similarly, the atoms will bend along the y-axis. Then two types of bending vibrations are possible. Now, a linear triatomic molecule has two bending vibrations that we have discussed just now, while a non-linear triatomic molecule has only one bending vibration. So this is a non-linear triatomic molecule, only one type of, that means first atom will bend towards this and the second atom will bend towards this. So only two types of bending vibrations. And only for non-linear triatomic molecule, only one bending vibration is there, and the only one bending vibrations are again divided into three types. That is called scissoring, rocking, wagging, and twisting. Scissoring, rocking, wagging, and twisting. That means four types of bending vibrations are possible. One type of bending vibration, and the bending vibration is divided again subdivided into four types. The first one is scissoring, rocking, wagging, and twisting. That is for non-linear molecule. So here we will discuss what is scissoring. Okay, so that is not there. So here we will discuss what is scissoring. So for scissoring, one will bend towards this just like a scissor. This is called scissoring. Then what is wagging? This is wagging. And then what is scissoring, wagging, and then what is rocking? This is called rocking. And then another one is twisting. Twisting means one of the atom, so all the two atoms, all the three atoms are present on a single plane. So for twisting, one atom will bend towards, one atom will bend below the plane and other atom will bend above the plane. That is called twisting. Now, for methylene group, that means CH2 group, the possible bending modes of vibrations are shown here. So here 3n minus 6 rule does not apply here because CH2 group is not a complete molecule. So here you can see this is asymmetric stretching. That means one hydrogen will compress and another will elongate. This is asymmetric stretching. And for symmetric stretching, both the hydrogen atoms will elongate. Now in bending, in plane bending, that is for scissoring, one hydrogen atom will bend towards this and another will bend towards this. So that is called scissoring. Now for twisting, one will bend below the plane and another will bend above the plane. That is called twisting. Now for rocking, the two hydrogen atoms will bend towards a single direction. For wagging, the two hydrogen atoms will bend out of the plane, that will bend out of the plane but in a single direction. So that is called wagging. But for twisting, they will bend out of the plane, but one will bend below the plane and another will bend above the plane. So these are the four possible bending vibrations for nonlinear molecules. Now coming to the complexity of the IR spectra of polyatomic molecules. In the light of the above discussion, we say that infrared spectrum of a polyatomic molecule which consists of an absorption band at each of the 3n minus 6 if the molecule is nonlinear and 3n minus 5 if the molecule is linear. That number of fundamental frequencies for nonlinear and linear molecules respectively, along with the corresponding overtones. So that means if the molecule is linear, then the number of fundamental vibrational frequency equals to 3n minus 5, and if the molecule will be non-linear, then the number of fundamental modes of vibration equals to 3n minus 6. Apart from that, again the molecule can also show first overtone and also show second overtone. However, in addition, we may say that we may also have weak bonds due to combination of the two fundamental vibrations, that is called combination. So that means apart from the fundamental first overtone and second overtone, if the molecule will be a complex molecule having complex structure, apart from the three different types of vibrational modes, other vibrational modes are also possible, that is called combination bands or different. So the combination bands arises due to difference in the fundamental, that is called a difference bands, and the combination band arises due to combination of two fundamental vibrations, that is called combination bands, and or the difference of by combination of two fundamental vibrations, that will give rise to another band, that is called combination band, and the difference of two fundamental vibrations, that may also give rise to another band, that is called a difference band. If the molecule is a simple molecule, that will show three bands: fundamental and the overtone have the frequencies very close to each other. This may resonate, leading to appearance of signals of different frequencies, higher or lower, relative to the original. That is called as Fermi resonance. This phenomenon is called Fermi resonance. That means apart from these five bands, if the fundamental and overtone have frequencies very close to one another, the molecule also show additional band, that is due to Fermi resonance. As the number of atoms in a molecule increases, the spectrum become quite complex. Now let us take the example of a larger molecule, say N-decane, that is C10H22, having 32 number of atoms. Hence, the number of fundamental vibrational modes will be 3n minus 6, that is equal to 3 into 32 minus 6, that is equal to 96 minus 6, that is equal to 90. So that means for n decane,
सब लेफ्ट हो गए?
हाँ, सब लोग चले गए, क्या हो गया अचानक से?
कुछ बताया भी नहीं।
हाँ, क्लास
वेट
क्या
कर लेते हैं, क्लास तो 8 बजे तक है।
हाँ, वही 8 बजे तक है ना क्लास, ना जल्दी कैसे खत्म होती है?
सर नेटवर्क कल बता रहे थे, नेटवर्क इशू शायद वो हो गया।
क्या हो गया?
कल नेटवर्क इशू बता रहे थे ना, कल आवाज भी नहीं आ रही थी,
हाँ,
तो वही हो गया।
बंद हुआ थोड़ी सी रिपट की।
Hello, hello.
हेलो सर।
Okay. So again, that was some disconnection due to some technical problem. So now we'll continue. Just wait. I am opening the material. So if we'll consider decane molecule, the total number of vibrational modes will be, because in the decane molecule the formula is C10H22, so the total number of atoms equals to 32. That means the molecule contains 32 atoms, and hence the total number of vibrational modes equals to 3n minus 6. That is a nonlinear molecule. So the total number of vibrational modes equals to 3n minus 6, that is equals to 3 into 32 minus 6, that is equals to 96 minus 6, that is 90. So if we consider the IR spectrum of complex molecule just like N-decane, that will show 90 number of different peaks or 90 number of different signals. Now coming to the characteristics of IR spectrum. So here you can see in the x-axis. So in the IR spectrum, the y-axis represents percentage of transmittance, where the x-axis either that will show the wave number or wavelength. It means that is the position of the IR absorption signals are presented in either wave number, nu bar, or that may be presented in terms of wavelength, that is lambda. So, but the y-axis represents the transmittance. The unit of the wave number is centimeter inverse, because we know that wave number is the reciprocal of wavelength. However, if we will put wavelength along the x-axis, then the unit of the x-axis will be micron or micrometer, because in incre- because an increase in it corresponds to increase in the energy, whereas the wavelength is related inversely to the energy. So this is a typical IR spectrum. You can see in this IR spectrum, the y-axis represent the transmittance, that means percentage of transmittance, and the x-axis represent the wave number in centimeter inverse. So this is the IR spectrum of a sample. Now coming to the basic components of the IR instrument. So the essential component of the IR instrument as follows. The first one is a stable and power source of radiation, and the second one is sampling device transparent to the radiation, and the third one monochromator or frequency modulator, the fourth one transducers or detectors, and the last one that is the signal processing and output device. So first we'll discuss what is the source of IR radiation, that means what is the source of infrared, that means which source will produce in electromagnetic radiation in the infrared range. So the best source available commonly employed in the IR spectrometers are, the first one is notched glowing filament lamp, notched filament lamp or glowing filament lamp, and the second one is globar, third one is nichrome wire, that is nickel chromium alloy wire, and the fourth one is carbon dioxide laser. So these are the source of IR spectra. So first we'll discuss North Glower. It is a cylindrical rod made up of a mixture of zirconium, yttrium, and erbium oxide. Again, it is a cylindrical rod made up of a mixture of zirconium, yttrium, that is made up of a mixture of zirconium, yttrium, and erbium oxide. It is electrically connected with platinum wire and heated by the passage of electrical current to a temperature of around
फिर से डिस्कनेक्ट हो गए।
उनका लगता है नेटवर्क इशू बहुत है।
हाँ 2 दिन से इशू आ रहा है, कल भी क्लास नहीं हो पाई थी, परसों भी नहीं हो पाई थी।
ये लगता है बारिश की वजह से डिस्टरबेंस बहुत ज्यादा आ रही है।
हाँ उस तरफ
सिग्नल
बारिश भी
नेटवर्क।
हो रही है।
हाँ। आप कहाँ से हैं?
मैं इधर से अलवर से।
एलो एलोर।
अ, दिल्ली से 80 किलोमीटर है।
अच्छा, दिल्ली।
हेलो।
हाँ, दिल्ली।
सर नहीं आए क्या अभी तक?
सर नहीं आया अभी तक।
क्या हुआ, कुछ बोले क्या आरसी से? कुछ इन्फॉर्मेशन आया?
वो
ये
इन्फॉर्मेशन
जो
नहीं आया, जैसे
क्लासरूम में
कल
आरसी
डिस्कनेक्ट
आते
हो
हैं।
रहे थे ना बार बार। जैसे कल
फिर
डिस्कनेक्ट हो
कल
रहा था ना
से
बार बार,
फिर
वैसे
से
ही हो रहा है।
10 मिनट से वो नहीं आया ना अभी तक।
ହ୍ୟାଲୋ ଅଭି ଯେଠି ମୁଁ କହୁଥିଲି ଆସିମି 3400 ଟଙ୍କା ନେଇ ମେଚ୍ ପାଇଁ ହେଲା କହିଛି ତମକୁ 3400 ଏ ମାସର ନେଇଛି 1700 ଆଉ ପୂର୍ବ ମାସର କ'ଣ ଥିଲା ବାକି କହିଲା।
So the next source of IR radiation, that is called global. Global, it consists of silicon carbide and length around 50 millimeter, which is electrically heated at about 1500 Kelvin, and the electrical contacts have a risk of electric arcing. Therefore, water cooling and Therefore, water cooling of the contacts is used. The spectral output is comparable with the Nernst glare except for short wavelength, where the output becomes larger. Now the next one is nichrome wire, that is incandescent nichrome wire. It is typically a coil of nichrome wire, nickel chromium alloy where it is electrically heated around 1100 Kelvin. It produces a lower intensity of radiation than the non-glare or global. And the next one is carbon dioxide laser. So it is a tunable carbon dioxide laser produce closely spaced discrete lines in a limited range of higher range around 900 to 1100 centimeter inverse. Then coming to the sampling devices. So the handling of the sample for the measurement of IR spectra is not simple. Firstly, because of so that is unlike UV visible spectroscopy, unlike UV visible spectrometry, glass or quartz cannot be used as a material for the making cuvettes to be used for the infrared region. It is so because that the glass absorbs strongly at most of the frequencies of this IR region, and secondly, the analysis of an analyte as a solution is not easy because most of the solvent of the organic compounds themselves are absorb many regions in the IR spectrum. So in the absence of glass, that means you cannot use glass or quartz cuvettes for just like UV visible spectroscopy. So in the absence of glass, salts like sodium chloride or potassium bromide, which are transparent in nature and that is transparent in the IR region, are used for the construction of cuvettes. So that means here the cuvette is made up of sodium chloride or potassium chloride. These cuvettes are called IR window. So that means we cannot make a complete cuvette for using sodium chloride salt or potassium bromide salt. So the sodium chloride windows are most commonly used for the routine work of the region around 650 centimeter inverse to 4000 inverse, as these are the cheaper window than potassium bromide. However, for the measurement, if you want to measure the IR spectrum below 650 centimeter inverse, then in that case you have to use KBR cell, and that is the right choice because the sodium chloride starts absorbing below this region. Now coming to, so the sampling technique depends upon the phase of the sample to be analyzed, that may be solid, that may be liquid or gas. So first we'll discuss, if your sample is a gas sample, what is the technique. So the first one is sampling of gases. The gaseous samples are taken in approximately 10 centimeter long cuvettes having sodium chloride windows at either end as shown in the figure. You can see, so this is the figure. In this figure, you can see, so that is a cylindrical cuvette, and both the windows are made up of sodium chloride. And the path length of the cells are easily varied over a long range. So in these typically designed cuvettes, the internal surface are made reflective, whereby the radiations can made to travel. That means the infrared radiations are made to travel through the sample many times before coming out it. So this is the sampling. So the figure A. So this is the sampling device for the gaseous substances, and the figure B. So the figure A, both this figure A, that is the sampling devices for gaseous substances, and the figure B represent the sampling device for liquid substances. Now for liquid samples, cuvettes with fixed path length as well as variable path lengths are commercially available. The cuvettes are less than 0.01 millimeter thickness are made of sodium chloride or potassium bromide. If you want to analyze your sample between 650 centimeter inverse to 4000 centimeter inverse, then cheaply you can use potassium chloride. But if you need the measurement below 650 centimeter inverse, definitely you have to use the KBR cell. Now coming to sampling of the solid substances, the most of the organic compounds observed extensively in the mid-infrared region. It becomes difficult to find a suitable solvent whose signals would not interfere with the signals of the sample. So in such cases, it becomes almost essential to analyze the solid sample itself. There are two techniques for handling solid substance. The first technique, that is mole technique, and the second one is pelleting with KBR. So first we'll discuss what is mole technique. So in this technique, nozzle mole technique, that is the sample is finely sample is finely ground to a paste in a small amount of mineral oil. The mineral oil may be the mineral oil is hexachlorobutadiene, that is called a nozzle, and it forms a fine suspension or a mole of sample in the oil. The mole is pressed between two NaCl or KBR plates to give a thin film of the sample. The two plates are then clamped in a holder with open windows both sides and assembly to keep in the path length of the infrared beam. And the next technique for the solid substances, that is KBR pelleting. So in this technique, a small amount of the sample, around 1 to 2 milligram, is mixed and ground with about 100 times more, 100 times of its mass of potassium bromide, and the mixture is transferred into an evacuated dye. So this is the dye. So that means you have to make a thin pellet, thin transparent pellet, and that thin transparent pellet will be placed through the window where the infrared will pass. Now coming to monochromators or frequency modulators. Monochromators which disperse the radiation from the source falling on it, and that can be used to allow the radiations of different wavelength come out of the exit slit. And then coming to the modulator of the signal is achieved by interferometer, Michelson's interferometer, the modulators of the frequency of the IR spectrum into the audio frequency range. So the fluctuations of the intensity of the audio frequency range are then followed by suitable transducers. This results modulated time domain signal which contains all the information about the spectrum. This is then the Fourier transformed to retrieve the information of the frequency domain. Now the transducer or detectors. So three categories of transducers are employed for detecting the IR radiations. So these are thermal transducer, that is called thermocouple or bolometer, and the next one is pyroelectric transducer, and the third one is photoconducting transducer. So first one is thermal transducer. So in the thermal transducer, there are in the thermal transducer. So as the name as the name suggests, so that will depends upon the thermal effect. There are two types of thermal transducer. The first one is thermocouple and the second one is bolometer. The thermocouple consists of a pair of junction of different metals. For example, the two pieces of bismuth fused to either end of the piece of the antimony. So the infrared radiations are made to fall on the junction, that is called the hot junction, and the other junction is called the cold junction, that is kept at a constant temperature. The difference in temperature causes an electrical potential difference between the two joints, and its value would depend on the difference in temperature between the two junctions, and the potential difference thus would depends upon the amount of the radiation falling on the hot junctions, and therefore there is a measure in the radiation. And the next one is bolometer. So the bolometer, that is a kind of resistance thermometer. So these are prepared using thin strips of platinum or nickel. So where so there is a metallic conduct. So metallic conductor change. So there is a change in metallic conductor with temperature. These materials show a quite large changes in the resistance of the on changing with the temperature. When IR falls on the bolometer, its temperature changes and causes a corresponding change in its resistance. Now coming to the pyroelectric detector. So so these are temperature dependent capacitor made from a single crystalline wafer of a pyroelectric material, and the pyroelectric material may be triglycerin sulfate, and the heating effect of incident IR radiation causes change in capacitance of the capacitor, which in turn can be measured in the external circuit as current. Now coming to pyroelectric transducer. So these are mercury cadmium telluride transducers and comprises of a film of semiconducting material deposited on a glass surface which is sealed in an evacuated envelope. So this is similar to the PMT or photomultiplier tube, so that is used in UV visible spectrometry. Now, in this photoelectric transducer, absorption of higher radiation by them causes electrical resistance of the semiconductor to decrease, which can be measured. And now coming to the signal processing and output device. So the electrical signal from the transducer is suitably amplified and processed before it is sent to the recorder to give an output. The dispersive IR instrument. So an optical null system is employed to achieve equal intensity of the sample and to the reference material. And the mechanism of processing the signal to give the recorder output. So here that will discuss here. So here the next one is instruments for IR spectrometry. We know that the IR region of electromagnetic spectrum spreads over wavelength range 0.8 micrometer to 1000 micrometer, and the wave number, so if you convert the wavelength into wave number, so that will be roughly from 10 centimeter inverse to 12,500 centimeter inverse. It is bound by red end of the visible region at lower wavelength, at a lower wavelength end, and the micro, so that means that will start from the red end of the visible region to the starting end of the microwave region, and hence the IR, so you can see this is the visible, so the red end of the visible region to the starting end of the microwave, and here the infrared is again divided into three different parts, that is near IR, which is due to the, so that is also called the overtone region, and the mid IR, that is called vibrational rotational region, and that is the, and then the next one is far IR, that is called only rotational region. So there are three types of IR in, so there are three types of instrument, infrared instrument. So these are, the first one is dispersive infrared spectrometer. The next one is Fourier transform IR spectrometer, and the next one is non-dispersive IR spectrometer. So first we'll discuss what is dispersive IR spectrometer. So these instruments are roughly outdated now, so that, so this instrument is not employed nowadays. So this is the schematic diagram showing the different components and the optic path of a dispersive IR spectrometer. Now coming to the FTIR, that's called Fourier transform infrared spectrometer. So in the Fourier transform infrared spectrometer, the signal from the sample is dispersed and response to each wavelength is measured individually. The FT instrument collects the response at all wavelengths simultaneously. In these complex instruments, the monochromator is placed by an interferometer, and these response and the response of the sample to the whole range of the IR is suitably modulated and collected in time domain. So these are decoded using the Fourier transformation. That's why the name of the instrument is Fourier transform infrared spectrometer, that is FTIR. So this is the schematic diagram of FTIR. Now coming to the next one. So these are the advantages and disadvantages of the FTIR. Now coming to, and the third instrument that is not so required for you. So if in your exam you will find the two different types, that is dispersive infrared spectrometer and the construction of dispersive infrared spectrometer, and the next one is FTIR spectrometer. Now coming to application of infrared spectrometer. So it has two different applications. First one is qualitative application. So in the qualitative application, it is important for the elucidation of structure of organic molecules, and for elucidation of structure of organic molecules, the scanning range is, so there are two different types of scanning range. The first scanning range, that is from 3600 to 1200 centimeter, that is called the functional group region, and the another scanning range, that is below 1200 centimeter to 400 centimeter inverse, below 1200 centimeter inverse to 400 centimeter inverse, that is called fingerprint region. The two regions put together are important in the determination of identity of a molecule, and the most, it is most impossible to assign all the possible frequencies observed in the IR spectrum. However, the identification of the characteristic picture of the functional group, including the stretching vibrations, bending vibrations of all type of organic molecules, so that can be measured. So in this table, so these are the characteristics IR frequencies of the some functional groups. So that means first here you can see if the functional group is alkane, that is only carbon hydrogen bonds are there. So in the structure, IR absorbing bonds and the frequency range is 3000 to 2800. Now for alcohol, the IR absorbing bond is oxygen hydrogen bond, and here that is a broad band in the frequency range of 3600 to 3200. Similarly, for amines, the IR absorbing bond is nitrogen-hydrogen bond. So that will show three different bands. First band is so due to 3500 to 3300 centimeter inverse, and the another two bands that you will observe from 3500 to 3300 centimeter inverse. So that is so these are the stretching bands, and the bending band for that you will observe in 1650 to 1560 centimeter inverse. And similarly, in this table, you have to remember for a particular functional group of organic compound, what is the IR frequency range and what are the possible modes of vibrations. Now coming to quantitative application. So in the quantitative application, in case of IR spectrometry, it is quantitative used to a number of practical and instrumental problems. So some of these are narrowness of the IR band, low intensity of the source and low intensity of the transducer, non-availability of the matched cell of the sample and reference, interference by solvent or IR absorbing air contaminants. So now we will discuss some clinical and biological applications. IR spectroscopy has been employed for the analysis of several analytes in the different biofluids and some biological samples. These are the application in the analysis of pathological samples for the diagnosis of for the diagnosis purpose and for the non-invention of in vivo monitoring. For example, particularly the mid IR spectroscopy has been used for analyzing facial fat contents and for the determination of composition of urinary and gallstones. And similarly, so these are the other biological and clinical applications. So now we will discuss the next chapter, that is called Raman spectrum. The next one is Raman spectrometry. So first we'll discuss the theory of Raman spectroscopy. An electromagnetic radiation, when passed through a transparent medium, interact with the particles, that may be atoms, ions or molecules. If the dimension of the particles are equal or smaller than the wavelength of the electromagnetic radiation, again, if the dimension, that means if the size range of the particles are equal to or smaller than that of the wavelength of the incident light, then it undergoes scattering. Again, I am telling, so this is not one type of absorption, this is scattering. So, if the dimension of the particle are equal to or smaller than the wavelength of the electromagnetic radiation interacting with it, then it undergoes scattering. It has been observed that most of the scatter radiations have exactly same wavelength that of the incident radiations. Then such type of scatter radiations are referred as Rayleigh scattering. However, a very small fractions of the scatter radiations is having found to be different wavelength than that of the incident radiation. So these scatter radiations or these type of scattering is called Raman scattering, and the existence of Raman scattering is called Raman effect. So here in this figure, you can see in this figure, the figure gives the spectra of the scatter radiation obtained when the samples of carbon tetrachloride was interacted with laser beam having a wavelength of 488 nanometer. So this is the figure of Raman spectra of carbon tetrachloride when the molecules of carbon tetrachloride interact with a laser beam which produces electromagnetic radiations of 488 electromagnetic radiations of wavelength 488 nanometer. So here you can notice the intense peak at the center of the spectrum has the same wavelength as that of the incident radiation. So here that is having the same so radiation as that of the incident. So radiation that is called relay scattering. So this is the relay peak, and the other signals on either side of the relay peak are called Raman lines. The lines on the left side of the relay peak having lower value of the wave number than that of the so relay lines. So these are called Stokes lines, and the lines which is having higher value of wave number than that of the so relay lines are called anti-Stokes lines. So Stokes lines are at lower energy while the anti-Stokes lines having greater energy than the relay peak. So the position of the Raman lines is expressed in terms of Raman shift, that is del nu bar, which defined as per the following. So del nu bar equals to nu bar of the scattered radiation minus nu bar of the incident radiation. That means, so that will give rise. So if there will be difference in the wavelength of the wave number of the incident radiation and different radiation, incident radiation and scattered radiation, then that will show Raman effect. And generally, the wave number of the incident radiation will be similar to than that of the scattered radiation. So that is called Surrey peaks. So here in this figure you can see, so the x-axis is the wave number or the Raman shift, that is del nu bar. So here you can see that so these are the peaks obtained having due to so relay scattering, and these are the peaks obtained due to Stokes lines, and these are the peaks obtained due to anti-Stokes lines. So there are two theories of Raman effect. So these are two different long questions. The first one is quantum or particle theory of Raman effect, and the second one is classical or wave theory of Raman effect. So first we'll discuss the quantum theory of Raman effect. So an electromagnetic radiation is considered to be consisting of streams of particles called photons, and the photons constituting radiations of frequency nu would have energy equal to h nu, where h is the Planck's constant. The interaction of radiations with interacting species can be visualized in terms of collision between them and the photons. If the collisions are elastic collisions, then the photons would be scattered with their incident frequency remain unchanged. So for elastic collision, the photon will scatter having same frequency or same wavelength. This explains the observance of relay lines in the spectrum. Since most of the collisions are elastic in nature, most of the scattered photons would have the same frequency as that of the incident frequency. Therefore, the relay lines observed are quite intense in nature. Now, next, a small fraction of the collision between the photons and the particles or a matter is found to be inelastic in nature. This involves exchange of, so that means if the if the collision between the incident electromagnetic radiation and the particle is inelastic collision, then that these involve exchange of energy. Now, when photons constituting radiations undergo inelastic collision with observing species, they either gain or lose energy. So, these energy exchanges bring about the transition in the quantized energy levels of the molecule. In such an event of inelastic collision, the molecules are either vibrationally excited or they may undergo vibrationally relaxation. In both of these, the photons get scattered with frequency different from that of their incident frequency. In the former case, that means in case of In case of vibrational excitation, when the molecules undergo vibrational excitation, they are of lower frequency, and in the latter case, which the molecules will undergo relaxation, the scattered photons are of higher frequency. So, When electromagnetic radiation interact with the molecule and the molecule will undergo excitation, then the scattered photons gives rise to Stokes line, and if the molecules will undergo relaxation, then the scattered photons will give rise to anti-Stokes Raman lines. So the figure 4.2 gives a schematic energy level diagram for a molecule. The set of the lines at the bottom represent the electronic ground state and the corresponding vibrational state. So here in this figure, so these are the ground state electronic level, and these are the vibration. So these are excited state electronic level. So if the scattered photons having same frequency or same wavelength or same wave number that of the incident line, then that is called Rayleigh scattering. And if they will undergo excitation, that will that may undergo excitation, and for if they will undergo excitation, that will show Stokes lines, and for relaxation, that will show anti-Stokes lines. And when the radiation having a wavelength that is different from any of the absorption maxima of the molecule interact with the molecule, the energy of the molecule increases by an amount that is h nu, and the energy changes can be represented by upward arrow or far left in the figure. This suggests that the molecule in the lowest vibrational state, electronic ground state, get excited to a virtual state, and the second arrow from the left represents the situation in which the incident photon encounters the molecule in its first vibrationally excited state, and accordingly virtual state has higher energy. So these are the mechanism by which we can get Stokes lines, anti-Stokes Raman lines, Stokes Raman lines, and Rayleigh scattering. So this is the quantum mechanical explanation. After that, again we will discuss the classical or wave theory. So for classical or wave theory, first we will discuss the polarizability of a molecule. When a molecule is placed in a static electric field, positive and negatively charged particles constituting in the molecule get attracted to the opposite poles of the static applied field. This leads to change in separation and consequently development of an induced dipole moment. Suppose if any molecule will be present in static electric field, then the positive part of the molecule will attracted to the negative part of the static electric field, and vice versa. So the molecule will undergo so the molecule will develop one type of dipole moment that is called induced dipole moment. In simple word, we say that the molecule has become polarized. This tendency of a molecule to get polarized is called polarizability. That is the ability to get polarized. The magnitude of the induced dipole moment is proportional to strength of the applied field, and here this is the magnitude of induced dipole moment mu is proportional to the strength of applied field E. So mu is directly proportional to E, or we can say mu equals to some constant alpha into E, where alpha, that is the proportionality constant alpha, that is called polarizability. It is the measure of the ease with which the molecule can get polarized. A weaker bond with loosely bound electrons are more polarizable, and a single bond is more polarizable than the double bond between the same set of atoms. Further, the polarizability can be anisotropic, that the electrons of a bond may be polarized to different extents when the field is applied in different directions. For example, hydrogen molecule get polarized to different extents when the field is applied in the direction of the bond or in the direction perpendicular to this. So this is the schematic representation of anisotropic polarizability of a molecule. So that means the molecule may be polarized in this direction, this type of, or this type, or another type of polarization. So what will happen if we place a molecule in an oscillating electric field? So now here we have discussed if we place the molecule in static electric field. But if we place a molecule in an oscillating electric field, that means the electric field will change its poles frequently. Then the electric field associated with the radiation having a frequency nu Ex varies as following equation: E equals to E naught cos 2 pi nu Ext, where E is the electric field strength at any time t. E naught is the amplitude of the wave. When such a radiation is made to interact with the molecule, it will induce a dipole moment in further. As the electrical field of the radiation is oscillating, that result induced dipole moment. That will also oscillate at the same frequency as that of the radiation. So mu equals to, which is equal to alpha E, equals to alpha E naught cos 2 pi nu ext. So the oscillating dipole would immediately generate a radiation of frequency just stay for 2-3 minutes. Okay, so the molecules are never stationary and always undergo vibration motion. So these motions may be cause a change in polarizability of the molecule. For example, the process of vibration bond length of a bond of of the molecule keeps varying, and the polarizability depends upon the strength of the bond. It may change the polarizability of the molecule. It can be shown that when such a molecule vibrates, the frequency nu vibration interact with the oscillating electric field of the electromagnetic radiation. Then the scattered radiation may have three different components. One of these component having frequency equals to that of the incident radiation nu ex. So these are due to so these are called so, so these are called as serial scattering, and another one having frequency more than the incident frequency nu ex, so that is nu ex plus nu vibration, that is due to anti-Stokes lines, and the another one is having lower frequency nu ex minus nu vibration, that is due to Stokes line. So this is the classical theory of Raman effect. Now coming to the very important part, that is Raman activity of vibration. So the Raman and IR spectra of a sample of molecule of CCl4 is given in this figure. Carbon tetrachloride is given in this figure. You may note that only some of the signals are common to the two spectra, and also common signals are in the different relative intensity. So you can see, so this one is the IR spectrum of the carbon tetrachloride molecule, and this is the Raman spectrum. Again, you can remember in the previous unit, IR spectrometry, in IR spectrometry, that all the possible vibrational modes of the molecule may not be IR active. Only those modes which have an associated change in dipole moment are IR active and show up spectrum, while the other two modes are absent. As mentioned above, in the Raman spectrum, only those vibrational modes are inactive which are associated with a change in polarizability. So due to this difference in the requirements for showing the two types of spectra, the IR and the Raman activity of the vibrational modes may be different from each other. The Raman activity difference of the vibration, the Raman activity of different vibrational modes can be predicted on the basis of whether or not the polarizability change during the vibration. If however, it is not very simple or in many of the cases. So so these are the IR and Raman activity vibrational modes of water and carbon dioxide molecules. So initially we have discussed the different vibrational modes for water molecule. So the first one is symmetric stretching, which is infrared active but Raman inactive. The next one is bending, which is infrared active, Raman active. The next one is asymmetric stretching, that is infrared active, Raman active. And for carbon dioxide, so the three vibrational modes, first one is symmetric stretching, Raman inactive, IR inactive, Raman active. For bending vibrational modes, IR active, Raman inactive. For asymmetric stretching, that is IR active, Raman inactive. Now coming to rules of mutual exclusion. So the rule is, for a molecule having a center of symmetry, the Raman active vibrational modes are IR inactive and vice versa. This is called rule of mutual exclusion principle. That is called mutual exclusion principle. And the rule of mutual exclusion says that if a molecule having a center of symmetry, that means if center of symmetry will be there, the modes which are Raman active are IR inactive, and similarly the modes which are IR inactive are Raman inactive. That is called mutual exclusion principle. Now coming to the instrumentation for Raman spectroscopy. So the five components of the Raman spectrometer. So there are five components. The first one is an intense laser source. The second one is a sample handling unit. Then monochromator or interferometer. Then detector. Then signal processing and output device. So here this is a schematic representation of the experimental setup of a dispersion Raman spectrometer, and this is the schematic representation of experimental setup of FT Raman spectrometer. So first we'll discuss what are the different radiation source for the Raman spectroscopy. Now these are the commonly used radiation sources in the Raman spectroscopy and their characteristics. So the laser source are argon ion having wavelength, frequency, wave number in this range. Then krypton ion. So these are the laser source which are used as the radiation source for Raman spectroscopy. Then helium neon, then diode laser, then neodymium YAG laser. First, then coming to the sampling handling device. So the Raman spectrometer has distinct advantages over the IR spectrometry because it permits the use of glass for holding of aqueous solution, So the possibility of using aqueous samples, the possibility of using aqueous sample is particularly important as it allows water pollutant besides that of biological and inorganic samples. More so, since the laser source are provided a focused coherent radiation, the sample container can be very small, which in turn required exceedingly smaller sample volume. So these are the transducers, so different parts of the Raman spectrometer. Now coming to the enhancements of the Raman spectral intensity, that is called a resonance Raman spectrometer. So at the Raman that is RRS, that is called a resonance Raman spectrometry. In the normal Raman spectral measurement, the spectrum is obtained by irradiating the sample in a region where it does not have absorption bands, and generally green, red, or near infrared lasers are used for this purpose, and the wavelengths are below first the electronic transition of the most of the molecules. The situation, however, changes when the wavelength of the exciting laser lines close to the electronic absorption of a molecule. Under these conditions, a resonance occurs which may enhance the intensity of few of the Raman lines in terms of 10 to the power 6 to 10 to the power 2 to 10 to the power 6 times. This phenomenon is called as resonance Raman spectroscopy or RRS. Now coming to another one, that is coherent anti-Stokes Raman spectroscopy, that is called coherent anti-Stokes Raman spectroscopy, that is CARS. So this technique uses two lasers, one of having a fixed frequency nu1 and the other having a lower frequency nu2. When combined with two lasers, as a result of coherent radiation of a frequency equals to 2 nu1 minus nu2. Besides, a number of other frequencies can also be observed. Then SCRS, that is called surface enhanced Raman scattering. For the surface enhanced Raman scattering, that will give intense Raman signals much later than the normally expected. So this technique, so again developed, and the Raman scattering from a compound or ion adsorbed on such a metal surface that can be 10 to the power 3 to 10 to the power 6 times greater in the solution. So the SCRS surface enhanced Raman scattering is found to be strongest in silver, but is observed in gold and copper as well. Though the exact mechanism of SCRS effect is not known till now, but that is the combination of chemical enhancement of polarizability of the bonds formed between the sample and the surface, and the electromagnetic resonance of the sample gold or silver particle. SCRS combined with RRS can give a large increase in sensitivity and the detection limit that may go down to nano, even picometer range. Now coming to application of Raman spectroscopy. So the Raman spectroscopy can be used for quantitative and qualitative analysis of inorganic, organic and biological samples. And the quantitative analysis is based upon the intensity of the Raman scatter lines being proportional to concentration, while the qualitative determination depending upon the wavelength shift being different for a wide range of different molecular vibrations. Since the Raman spectrum typically contains a number of well-resolved spectral bands, the information available for the band position, intensity, shapes that constitute a unique fingerprint of the molecule that can be exploited for quantitative analysis. Now, organic compounds that contain functional groups with highly deformable electron clouds are good scatters than the radiation. Some important functional groups include alkenes, alkynes, cyano groups, and the stretching vibration of these functional groups gives rise to weak and undetectable IR signals. While in the Raman spectra, these are quite strong and can provide useful information about the environment of the group in a molecule. In addition, Raman spectroscopy is very useful for measuring symmetric vibration from carbon-carbon bonds uh, of the polymer and diatomic molecules like nitrogen, oxygen, etc., which are Raman inactive. So generally, we know that diatomic uh, molecules like N2, O2 are Raman inactive, infrared inactive. That means the molecule which does not possess any type of dipole moment are infrared inactive, but that can be analyzed through Raman spectroscopy. So after that, we will again we will move to the next technique, that is unit 5. So the unit 5 is fluorimetry and phosphorometry. So that we'll discuss on Monday. This unit 5 will discuss on Monday. Okay. So here we'll discuss the fluorescence and phosphorescence spectra. So that we'll discuss on Monday. Right? Hello.
ओके सर.
Okay.
Okay, sir.
Okay.
Hello. Hello.
हेलो.
सर चलेगी.
टाइम बना ली.
असाइनमेंट वगैरह क्या हुआ? क्या कुछ बनाया क्या?
मैंने अभी एक बनाया.
नहीं बनाया ना? स्टार्ट
एक
तो किया था
MCH
ना?
0 का बना लिया.
कौन सा वाला?
MCH 01.
खत्म हो गया वो वाला?
हाँ, पेपर 1 तो बना लिया मैंने.
अच्छा. आपका कहाँ? दिल्ली बता रहे थे ना, ये रीजनल सेंटर.
हाँ, मेरा रजिस्ट्रेशन दिल्ली है.
अच्छा. ये सर को क्या ग्रुप में ऐड कर दें क्या? सर को
इंसर का
बात
नंबर है.
करेंगे. नंबर तो नहीं है, बात करने से मिल जाएगा सर से. अच्छे से बात तो कर रहे हैं.
हाँ, जैसे भी इनका भी मैंने डॉक्टर प्रकाश साहू का नंबर लिया था ना.
हाँ हाँ हाँ. वो सर तो अच्छे से नोट भी दिए थे. मैं देख रहा था, उनका नोट भी अच्छा था.
हाँ, वो PPT मैंने मांगी थी इनसे.
ये
मतलब
कौन?
मांगने से दे दिए ना ग्रुप में.
जो हमारा सेकंड लेक्चर था अभी इससे पहले.
हेलो.
हेलो.
ये कौन सा ग्रुप है?
ये हम दोनों ने बनाया, कोई तो था नहीं ग्रुप में.
ओके ओके, बस आप दोनों.
हाँ, हम दो हैं और जो वो साहू सर है, तीसरा है.
हाँ सर. अच्छा. मुझे भी ऐड कर लो ना उस ग्रुप में.
आपका आपका नंबर भेज दीजिए.
ओके, आप
नहीं तो
नोट
मैं
कर लो,
आपको
बोल देती हूँ.
नहीं तो मैं आपको इनवाइट लिंक भेज देता हूँ. आप ज्वाइन हो जाएगा.
ओके ओके.
नीचे एक मैसेज में टाइप कर दो, मैंने नंबर टाइप किया.
हाँ, मैसेज में डाल दीजिए ना. मैं थोड़ा गाड़ी चला रहा हूँ.
हाँ ओके, मैं नंबर डाल देती हूँ.
मैंने
ओके, ये
सर को
मैंने
प्रैक्टिस
नंबर भेज
बोला
दिया
है.
है.
प्रैक्टिकल के लिए बोला था मैंने सर को, वो बोले शेयर कर देंगे प्रैक्टिकल डिटेल.
हाँ, मैं वही पूछने वाला था. प्रैक्टिकल वगैरह किससे करें? मतलब जाके करना है या फिर यही सर लोग बताएंगे? कुछ बोले क्या कोई?
ये
लैब
साहू
नहीं
सर की
होगा
बात
क्या?
की.
क्या
लैब
क्या?
होगा उधर? लैब कराते हैं उधर?
अच्छा.
आप लोग का क्या केमिस्ट्री से ही है आप लोग?
हाँ.
हाँ,
कौन
मैं
सा?
तो केमिस्ट्री से हूँ.
ओके ओके. अच्छा, बीएससी करके आप लोग ये डिप्लोमा कोर्स कर रहे हैं?
हाँ.
हाँ. आपने?
नहीं, मैंने एमएससी कर रखा है.
अच्छा.
अच्छा.
एमएससी के बाद में एक और डिप्लोमा कोर्स कर.
मतलब एमएससी के बाद मतलब जॉब वगैरह कर रही हो क्या? एमएससी
नहीं,
खत्म हो
जॉब
गया
नहीं.
है?
हाँ, एमएससी कंप्लीट हो गया है मेरा. जॉब नहीं कर रही
अच्छा.
हूँ, बस अभी एक और कोर्स करना था तो कर रही हूँ. एनएलआईटी का शायद से नहीं होगा ना प्रैक्टिकल इसका. इसकी मशीन्स नहीं होती है ना हर जगह.
हाँ, वही तो. क्या, मैं तो स्टडी सेंटर गया था समझने के लिए। स्टडी सेंटर में मेरे को मना कर दिया कि हम बोल नहीं पाएंगे क्या होगा क्या नहीं।
हाँ।
आपका तो एक टोटल मेरे को बोले कि मेरे स्टडी सेंटर में एक ही मैं लड़का हूँ, जैसे कि उनका स्टडी सेंटर में एक ही है, जितेंद्र जी का।
ओके, आप लोग कहाँ से हैं? वो तो बताए वो दिल्ली से हैं, और आप?
मैं उड़ीसा से।
अच्छा, उड़ीसा से हैं। ओके।
जी जी जी।
उसकी मशीन्स हर जगह नहीं होती है, बस रिसर्च सेंटर में ही रहता है। तो शायद हमारा लैब ना हो, या कुछ ना कुछ तो कराएंगे। कुछ पेपर तो करा देंगे।
बाकी साहु सर ये कहते जब प्रैक्टिकल जमा करने जाओगे ना, हाँ, असाइनमेंट जमा करने जाओगे तब बताया जाएगा आपको।
अच्छा।
प्रैक्टिकल वो
आप
1
वैसे कहाँ
सितंबर से
से,
30
कौन सा
सितंबर तक
रिजर्व
जमा करने
सेंटर?
हैं।
अच्छा अच्छा। जमा करने जाएंगे ना ना, ऐसे ये में भेज देंगे आपको, कोरियर कर देंगे।
कुरियर भी कर सकते हैं, वहां जाके फिजिकल हार्ड कॉपी जमा कर सकते हैं। मुझे तो इसके लिए वही चाहिए था, जैसे मैं बीएससी था ना,
हाँ
तो जॉब में
वही
बीएससी
वही।
को मशीनें चलाने नहीं देते।
हाँ, मशीन तो
क्या
हमारे
जॉब
कॉलेज
है
वगैरह
आपकी?
में नहीं होते हैं।
नहीं, मेरी कंपनी में है ये मशीनें।
अच्छा।
क्या जॉब है
आपका जो
आपकी?
था।
मैं पेंट इंडस्ट्री में हूँ।
पेंट इंडस्ट्री में।
जी।
बीएससी केमिस्ट्री करके।
हाँ,
आप जो
हम्म।
क्या 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 मशीन यूज करते हैं अभी के लिए, जैसे कि कौन
मैं
सा
एफ टी आई यूज करता हूँ,
और
HPLC।
मतलब कैसे, मतलब कौन से प्रिंसिपल में काम करता है, जैसे कि ये जैसे कि स्पेक्ट्रोफोटोमीटर वगैरह में काम करता है क्या?
हाँ, ये स्पेक्ट्रो फोटो जो आज जो क्लास पढ़ाई ना, FTIR।
हाँ 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 हाँ
हाँ, वो मशीन।
हाँ,
मतलब जो कलर से, जो मैं रॉ मटेरियल चेक करता हूँ कंपनी में कि इसी में क्वालिटी एग्जीक्यूटिव रॉ मटेरियल हूँ।
ओके, तो आप
हाँ।
स्पेक्ट्रोमीटर पे चेक करते हैं?
नहीं, स्पेक्ट्रो फोटोमीटर तो कलर चेक करता हूँ।
ओके।
FTIR पे हम उनकी पिक चेक करते हैं कि उसमें कुछ इम्प्योरिटीज तो नहीं है।
अच्छा अच्छा।
अच्छा।
और जो सॉल्वेंट्स होते हैं उनको हम GC पे चेक करते हैं।
जी इसी पे। ये सारे फिर प्रोसेस आपको क्या कंपनी में बताया गया? क्योंकि ये तो पीजी में भी बताते नहीं है, बिकॉज
ये पीजी में
स्पेक्ट्रोमीटर
बताते नहीं है।
पढ़ा देते, थ्योरेटिकल पढ़ाते हैं। ओके,
मैंने
उसके
कंपनी
बाद
में सीखा था।
वही कंपनी में आपको सिखाया गया है। ओके।
हाँ।
ग्रेजुएशन में भी है लेकिन ज्यादा नहीं है, पीजी में ज्यादा है लेकिन मशीन्स नहीं होती है यूनिवर्सिटी में, तो बस थ्योरेटिकल बताया जाता है हमें।
जो थ्योरेटिकल तो बताते हैं पर प्रैक्टिकल नहीं समझ, आसानी समझ में आता है।
हाँ, प्रैक्टिकल और थ्योरेटिकल कम्प्लीटली डिफरेंट होता है ना, तो मतलब जो थ्योरी में आप पढ़ रहे हैं प्रैक्टिकल में करना होता है, और उसके डेटा भी अलग ही रहता है। कभी कभी हमारा कंडीशंस पे भी हमारा एक्सपेरिमेंट इधर उधर हो जाता है। थ्योरी में उतना पढ़ाते नहीं मैं, बस एक मैनिपुलेटेड रिजल्ट रहता है, वो आना चाहिए, दैट्स इट। प्रैक्टिकल
मतलब
में
पीजी में क्या पढ़ाता है एक्चुअली में, जैसे
हाँ,
कि मतलब जैसे कि बीएससी में तो कुछ जैसे खास नहीं पढ़ाते हैं, वैसे थ्योरी पढ़ा के छोड़ देते हैं, प्रैक्टिकल को छोड़िए। मैं जितना, मेरे को जितना एक्सपीरियंस है, हमारा प्रैक्टिकल तो ऐसा ही नहीं हुआ था बोलने से। वैसे ही आपका था या फिर कुछ अलग था?
हमें भी ग्रेजुएशन में ज्यादा कुछ नहीं पढ़ाई, पीजी में बहुत डिटेल में पढ़ाई हुआ। और प्रैक्टिकल भी बहुत बहुत तरह के एक्सपेरिमेंट हमें होता था। एनालिटिकल हमें पढ़ाया नहीं गया है, हमारे इसमें एनालिटिकल ब्रांच था ही नहीं, तो इसलिए मैं अब अलग से एनालिटिकल कर रही हूँ।
पीजी में तो जैसे कि केमिस्ट्री पीजी में एनालिटिकल तो होता ही है ना, नहीं होता है क्या?
एनालिटिकल थोड़ा थ्योरी पार्ट रहता है, थोड़ा सा रहता है, लेकिन वो
वो
अलग
जो
तरीके
फिजिकल
से
केमिस्ट्री
डिवाइड
में रह जाता है।
है। इनऑर्गेनिक में थोड़ा सा आता है, थोड़ा फिजिकल में आता है, तो हम लोग को बस इतना ही। अब हमारा प्रैक्टिकल इनऑर्गेनिक, ऑर्गेनिक और फिजिकल पे होता था प्रैक्टिकल। तो एक एक सेमेस्टर एक एक प्रैक्टिकल, एक फर्स्ट सेमेस्टर में हमें फिजिकल हुआ, सेकंड सेमेस्टर में हमें ऑर्गेनिक का प्रैक्टिकल चला, थर्ड और फोर्थ में इनऑर्गेनिक रहा है। प्रैक्टिकल अच्छा डिटेल में बताया गया है।
बाकी हैंड ऑन प्रैक्टिस से अच्छे से आता है।
हाँ ये तो सही बात है।
पिपेटिंग अच्छे से आनी चाहिए, नहीं तो सैंपल फिर ह्यूमन एरर हो जाता है उसमें।
बहुत सारे ह्यूमन एरर होता है।
मशीनें तो बढ़िया आ रही है सारी, एजीलैंड की सबसे बढ़िया रहती है, पर वो कॉस्टली बहुत
कौन
रहती है।
कौन से?
एजीलैंड कंपनी की।
अच्छा।
वैसे मोस्टली तो जैसे मैंने जिन इंडस्ट्री में काम किया है उनमें सिमाजडू की है, वो थोड़ी कॉस्ट इफेक्टिव भी है और
जैसे कि
यूज करने में
आपका
भी
काम
आसान।
मतलब बोल रहे हैं कि कॉलर कैसे मतलब बनाते हैं, या फिर इंडस्ट्री कौन सा इंडस्ट्री है आपका?
जो मेरी कंपनी है वो कलर बनाती है, जो कि अपने फोम में, शूज में, और जो ऑटोमोटिव यूज होते हैं ना, जो गाड़ियों के डैशबोर्ड में कलर होता है,
हाँ।
उनके सीट कवर में, हैंडल में, स्टीयरिंग में, टायर में जो कलर होता है वो। आईएमसी
आपका
सुना होगा,
काम
इन
बस।
मोल्ड कोटिंग।
ये कुछ गैरेज वगैरह भी करते हैं वो वाला पुट्टी?
नहीं, गैरेज वगैरह नहीं, मेरा तो सीधा जैसे हमारा टीजीआई से टाई अप है, टीजीआई सभी गाड़ियों के लिए स्टीयरिंग और डैशबोर्ड बनाती है,
अच्छा।
तो टीजीआई को जो भी कलर जाते हैं वो हमारी कंपनी से जाते हैं।
बता
और
रहे
तो
थे।
ये बेंगलोर में कोमोस है, कोमोस किया की गाड़ियों को बनाती है। मतलब जो मेन जो कार कंपनी है उसी असेंबलिंग करती है। बाकी पार्ट्स अलग अलग कंपनी में बनते हैं, जैसे पैरागन जो है वो चप्पल भी बनाती है और वो केटीएम बाइक के पार्ट्स भी बनाती है। तो मेरा क्वालिटी में रॉ मटेरियल का डिपार्टमेंट दे रखा है मुझे, जितने भी आरएम आएंगे, पिगमेंट्स, ऑयल, सॉल्वेंट्स, रेजिन, तो वो सब चेक करने होते हैं।
मतलब आपका मतलब कितना डिपार्टमेंट होता है वगैरह जैसे उधर का?
जैसे मतलब हमने क्यूसी में 6 डिपार्टमेंट डिवाइड कर रखे हैं प्रोडक्ट वाइज। जैसे एक तो आरएम का कंबाइन कर दिया, सभी रॉ मटेरियल एक साथ ही आते हैं, मतलब एक जगह चेक होते हैं। और एक जो फोम के कलर होते हैं उनके लिए अलग क्यूसी पार्ट कर दिया हमने।
आपको टेस्टिंग का काम मिला हुआ है।
हाँ, टेस्टिंग का।
सैंपल वगैरह कैसे मतलब आपको आता है, मतलब बोतल वगैरह या फिर कुछ सैंपल कलेक्टर वगैरह कोई
सैम्पलिंग,
रहता है? हाँ हाँ। कैसे
हाँ
लाते हैं
सैम्पलिंग किट।
सैंपल वगैरह?
जैसे ऑयल से सॉल्वेंट आते हैं वो हम पाइप से निकालने वाला, उससे जेकअप से निकालते हैं। वो सैम्पलिंग टूल्स होते हैं अलग अलग, पिगमेंट्स के लिए अलग होते हैं, ऑयल्स के अलग, रेजिन के लिए अलग। उसके लिए 2 असिस्टेंट दे रखे हैं सैम्पलिंग के लिए।
आपका डेजिग्नेशन वगैरह मतलब क्या, केमिस्ट है या फिर एनालिस्ट?
मैं एग्जीक्यूटिव हूँ। मैं ये इसलिए कर रहा था, मेरे को फार्मा में स्विच करना था। मतलब
मेडिसिन या
मेरे घर के
फिर कोई
पास एक,
अलग इंडस्ट्री?
नहीं, मेरे घर के पास एक नई फार्मा कंपनी खुल रही है, तो मैं वहाँ स्विच करने का प्लान था मेरा।
हाँ, फार्मा फार्मा कंपनी भी एक अच्छा ऑप्शन है, बट ये पेन
नहीं,
इंडस्ट्री में प्रॉब्लम फिर ज्यादा होती है, बाद में फ्यूचर में प्रॉब्लम ज्यादा होता है, हेल्थ इश्यूज आते हैं पेन पेन तो फैक्ट्री में अगर काम करे तो। इसलिए
पेंट
गैस।
इंडस्ट्री में वो मेन इशू ये रहता है कि कंपटीशन को आप जा नहीं सकते। अब मैं इनके कॉम्पिटिटर में जा ही नहीं सकता, इसलिए मैं फिर स्विच करने का प्लान है मेरा। क्योंकि जो भी इनके कस्टमर हैं और जो इनके कॉम्पिटिटर है, उनमें मैं जा नहीं सकता, ये उन्होंने मेरे से बॉन्ड साइन करवा रखा है।
अच्छा।
तो फिर तो फायदा नहीं हुआ ना, फिर लंबा
हम्म,
टाइम है देने का। जैसे अभी करियर की स्टार्टिंग है, तो अभी तो चेंज कर सकते हैं, बाद में दिक्कत आएगी।
तो आपकी जॉब दिल्ली में है?
नहीं, मेरी भिवाड़ी में है।
कौन है?
भिवाड़ी।
रिवाड़ी?
हम्म।
ये दिल्ली के बाहर पड़ता है?
हाँ, एनसीआर में पड़ता है, क्योंकि दिल्ली से सारी कंपनियों को बाहर निकाल दिया ना पोल्यूशन के कारण।
अच्छा।
तो आता है एनसीआर में, पर भिवाड़ी एरिया में है। आपका रीजनल सेंटर कौन सा है?
मेरा तो हैदराबाद में।
हैदराबाद में।
मैं हैदराबाद से हूँ।
हैदराबाद में आया था मैं आगे पिरामल हेल्थ केयर के लिए।
क्या है?
हैदराबाद में आया था, जो पिरामल हेल्थ केयर है ना वहाँ पे,
अच्छा अच्छा।
उसमें मैं करके गया था 6 महीने।
अच्छा।
वो इंटर्नशिप थी मेरी वहाँ पे।
इंटर्नशिप हुई।
हम्म।
प्लेस जगह अच्छी है रहने के लिए।
यार मुझे खाना सूट नहीं करा वो, मुझे नॉर्थ इंडियन खाना चाहिए था।
साउथ इंडियन खाना सेट नहीं होता है जल्दी, खट्टा
एक तो
ज्यादा
बहुत
खाता है।
स्पाइसी रहता है, बहुत स्पाइसी रहता है।
हैदराबाद तो मशहूर ही है अपने खाने के लिए।
हम्म, रोटी तो वहाँ मिलती ही नहीं। मैंने खूब ट्राई, कई जगह ट्राई की।
ये रोटी की जगह पे यहाँ पे पूरी और पराठा मिलता है।
पूरी और पराठे सूट नहीं करते ना मुझे।
मुझे भी
अभी
बहुत
तो मैं वापस आ गया 6 महीने में।
नॉर्थ से कोई इधर आए तो इधर रहना बहुत मुश्किल होता है। खाने पीने का मेन
हाँ
खाने पीने का ही प्रॉब्लम होता है, और कुछ प्रॉब्लम नहीं होता है।
हाँ। तो दूध के लिए मेरा पैकेट दूध तो मिल रहा था, लेकिन
हाँ,
वैसे गाय भैंस का दूध बहुत ढूंढने के बाद मिला था। वो दे रहा था 150 रुपये लीटर।
150? बहुत एक्सपेंसिव दे रहा था, उतना ज्यादा महंगा नहीं है दूध।
अरे 150 रुपये
मैंने
लीटर बहुत ज्यादा होता है।
अरे वो उस टाइम दे
नॉर्थ
रहा था।
इंडियन में, नॉर्थ इंडिया में तो ये 60 60 रुपए में मिल जाता है, हमारे यहाँ 50 रुपए चलता है।
यहाँ
हाँ।
भी 80-85 ऐसे मिल जाता है भैंस का दूध। गाय का दूध भी वही कॉस्ट है। बहुत। आप कौन से एरिया में रहे?
मैं जो आर्मी कैंट है ना,
क्या कौन एरिया में?
कैंट एरिया, आर्मी कैंट।
हाँ हाँ, एनआर में क्या था? अच्छा, वो तो शहर से बाहर हो जाता है।
हाँ वही।
अच्छा अच्छा। तो उधर तो चीजें सस्ती मिलती है, फिर इतनी महंगी कैसे मिल रही है?
यार वो बाद में पता लगा ना, वो दूध मेरे को 150 दे रहा था, दूसरे को 80 दे रहा था।
अच्छा, पूछ रहा था। वो लैंग्वेज लैंग्वेज समझ गया होगा, बाहर के है।
हाँ इसलिए।
तो यहाँ पे वैसे ही
तो
होता
बाद
है
में पता
जैसे।
लगने के बाद फिर मैंने 80 पे लिया। शुरू में मैंने 150 पे लिया।
हाँ हाँ। यहाँ पे जो तेलुगु बोलता है उसको प्रायोरिटी मिलती है।
हम्म।
यहाँ पर अच्छे से देखते हैं कहाँ से है।
और मंदिरों के प्रसाद ही वो यहाँ से अलग मिलते हैं।
हम्म, यहाँ पे सब चीजें डिफरेंट होती है।
जैसे मैं सोचा तो मंदिर में खा लूंगा, प्रसाद अच्छा मिलेगा, उसमें भी वो अलग ही टेस्ट था।
इसमें नॉर्थ का भी अलग प्लेस है। वहां पर जाए तो हाँ, नॉर्थ इंडियन से मिलता है वहाँ पे बिल्कुल। सब चीजें नॉर्थ इंडियन वाली ही रहती है। जैसे कि हाईटेक सिटी है, पोपट चिल्ली और टोली चौकी, इन सब में नॉर्थ इंडियंस बहुत ज्यादा है।
हम्म।
वो एरिया हम लोगों के लिए ठीक है। लेकिन इस बाकी दूसरी तरफ ना साउथ इंडियंस जहाँ पे ज्यादा होते हैं, वहाँ पे पूरा तौर तरीका इन लोगों का अलग रहता है। ओके देन, मुझे
इसके
ग्रुप
कुछ
में।
नोट्स नोट्स बनाए?
नोट्स तो कुछ नहीं, बस असाइनमेंट का है, बस उसी से पढ़ ले रही हूँ।
असाइनमेंट हो गए
वो
पूरे?
नहीं, पूरा काम हुआ है, एक ही हुआ है। MCH-001।
मेरा वही हुआ है।
टाइम नहीं होता है वो, क्वेश्चन भी बहुत ज्यादा है।
हाँ लेंथी क्वेश्चन है मेरा।
सितंबर 30 है ना उसका
लास्ट
लास्ट
डेट
डेट?
है। पर वो
लास्ट
है
डेट।
कि 5 से सितंबर में अगर असाइनमेंट जमा नहीं करोगे ना तो एग्जाम के लिए अप्लाई नहीं कर पाओगे। तो ट्राई करो
हाँ
20 से पहले जमा करो,
हाँ।
ताकि वो असाइनमेंट के लिए, एग्जाम के लिए फॉर्म अप्लाई कर सकूं।
ये ई ज्ञान को खुल नहीं रहा है ना आपका, ये जो एप्लीकेशन?
हाँ वो खुल ही नहीं रहा है।
मैं हर बार ही चेक
तो
करता
उसकी
हूँ,
वेबसाइट
कभी
से
भी
कर लो।
नहीं। हाँ,
ऐप नहीं
वो
खुल रहा इसका,
वेबसाइट
वेबसाइट
देख
से
रहा
चेक
था,
करो।
वेबसाइट थोड़ा मतलब दिक्कत देता है ना, इसलिए मैं सोचा कि एप्लीकेशन वगैरह में सही होगा।
नहीं, एप्लीकेशन में प्रॉब्लम आ रही है। मैंने भी ट्राई किए थे 3 4 बार, पर ओपन ही नहीं हुए। मैं इसकी वेबसाइट से कर लेता हूँ।
आप तो मतलब डाउनलोड तो होगा ही ना, और जो नोटिफिकेशन वगैरह कहाँ चेक करते हैं?
नोटिफिकेशन इसके आते रहते हैं, जो
मेल
स्टूडेंट
पे?
पोर्टल पे।
अच्छा।
मेल पे भी आते रहते हैं और मैसेज भी आता रहता है।
मेल तो
मतलब
आते ही रहते हैं,
हमारे
छोटी छोटी चीजें मेल कर देते हैं ना। तो उसका पोर्टल कभी खुलता है कभी नहीं खुलता है।
वही वही दिक्कत है। और एक
मैं
मतलब कोर्स गाइड नहीं है ना, प्रॉब्लम यही है। मैं देखा है कि ये कोर्स गाइड कुछ होते हैं, कोर्स गाइड करके इग्नोर में।
ऐसा कुछ नहीं, इग्नू में ऐसा कुछ नहीं रहता। खुद ही करना पड़ता है, सारा सेल्फ स्टडी रहता है।
हाँ, सेल्फ स्टडी रहता है, पर कोर्स गाइड कुछ रहते हैं, जैसे कि काउंसलर वगैरह के कुछ रहते हैं।
वैसा इसमें है नहीं। इग्नू से इस उम्मीद मत करो ऐसी।
अरे मैं तो उम्मीद ही छोड़ दिया था, ये जो 6 महीने बाद ही क्लास 2 स्टार्ट हुआ है ये वाला।
हाँ, वो तो मैंने तो असाइनमेंट डाउनलोड कर ली थे, उसमें लिखा था कि जब आपको असाइनमेंट मिले तो उसके 12 महीने हफ्ते बाद जमा कर दो, सितंबर तक का वेट मत करो।
अच्छा,
आपको कब मिला है असाइनमेंट? मुझे तो मई में मिला है।
नहीं, मैंने जैसे असाइनमेंट, मेरा एडमिशन कंफर्मेशन का मेल आया था,
हाँ हाँ
तो उसी में जो बहुत सारे लिंक थे, उसी में असाइनमेंट का लिंक भी था।
हाँ। हाँ, मुझे मुझे बाद में आया था मेल। अप्रैल में आया
देखो,
मुझे कंफर्मेशन मेल, उसके बाद मई में आया असाइनमेंट का मेल।
असाइनमेंट का मेल भी आता है क्या? मेरे को तो
जो
नहीं।
एडमिशन कंफर्मेशन का मेल आया ना, उसमें सारी वेबसाइट दी हुई है।
हाँ, वो तो वेबसाइट ही दी गई है जो बोल रहे हैं
तो
कि।
उन्हीं को ओपन कर करके करो।
हाँ हाँ, वो तो मैंने देखा था, मैं असाइनमेंट देखा था। चालू नहीं किया है अभी तक, ये दिक्कत है।
चालू करो, वो बहुत लेंथी है।
लेंदी है ना?
सभी क्वेश्चन
हम्म,
करना पड़ेगा, क्वेश्चन बहुत ज्यादा है ना।
असाइनमेंट के सारे करने पड़ेंगे, असाइनमेंट में ऑप्शन नहीं है। पेपर में 5 करने पड़ सकते, पेपर में 5 करने हैं, बाकी असाइनमेंट तो सारे करने हैं।
30 मार्क्स के लिए बहुत क्वेश्चन है, 30% ना इसका।
हाँ, लेकिन वो पेपर तो 100 मार्क्स है असाइनमेंट का।
हाँ, 100 मार्क्स का पेपर ही है बस।
ना, जो
30%।
असाइनमेंट जो पेपर है वो भी 100 मार्क्स का है।
अच्छा।
हाँ, वो एक पेपर 100 मार्क्स का है।
मैं तो अब खींचूंगा असाइनमेंट। 2 दिन छुट्टी है, फिर अगले अगले हफ्ते भी 3 दिन छुट्टी, फिर 5 दिन छुट्टी में कंप्लीट करना पड़ेगा। एक कंपनी से लीव तो ले ली मैंने असाइनमेंट के नाम पे। कंपनी में और जमा करने पड़ेंगे, एक असाइनमेंट बना रहा हूँ। स्टडी लीव मिल जाती है।
ओके,
आपको?
स्ट्रेटजी।
हाँ, लेकिन उसमें क्या है, मुझे डेली रिपोर्ट करना पड़ता है कि मैंने अपनी स्टडी में क्या किया।
अच्छा।
अगर वो रिपोर्टिंग नहीं करूंगा तो वो लीव मेरी कैंसिल कर देंगे। चलो ठीक है फिर।
ओके
ठीक है, आपको ग्रुप में ऐड
मंडे को
कर दिया
मिलते हैं।
है, देख लेना।
ठीक।
ओके, मैं देख लेती हूँ। थैंक यू। बाय।
बाय।